Right then, this is the final video for the year, and it is all about the photoelectric effect. Now, before you watch this video, you should have gone on to the simulation on PhET, which is the photoelectric effect one. And what I'm going to do is just have a little play with it before you watch this video. Otherwise, what I'm going to say won't make a great deal of sense. What you should have found when you watch the video is that you have a light that you can change the intensity of, and you can change the wavelength of light that it emits, and it's shining onto a metal plate that's basically in a vacuum photocell. And the metal plate, when you shine a light on it, sometimes electrons are emitted, sometimes they aren't. And it's just from the light being shone on the metal plate that we can emit those electrons. And that is the photoelectric effect. That's the experiment that was performed by Einstein when he uncovered this. So the things you hopefully should have observed from just having a little play around is that you should have found that there was kind of a magic frequency, and it was the frequency that decided whether or not the electrons were emitted. And we only got electrons being emitted when you went above the threshold frequency, this magical cutoff frequency. Hopefully you also tried changing the materials, in which case you would have found that that cut-off frequency, that threshold frequency, was different depending on the material that you were shining the light onto. If you change the intensity, what you should have found is that changed the number of electrons emitted, but only if you're above the threshold frequency. So if you were below the threshold frequency, it wouldn't matter how high the intensity was, you still wouldn't get any electrons off. But once you pass the threshold frequency, changing the intensity changed the number of electrons that were released. Hopefully you noticed that if you're above the threshold frequency, the electrons were emitted immediately. There was no delay, it didn't matter how long you waited. And you should have also been able to notice the speed at which the electrons went, and the speed at which the electrons was released would depend on the frequency. So higher frequency led to faster electrons. So hopefully those are things that you should have observed. Now, all those things are very difficult to explain if we are treating light as a wave. Now, up until this experiment, it was kind of common knowledge that electromagnetic waves were waves. They behaved like waves. They were just waves. There'd been a huge debate raging for a very long time in the physics community about this, but it was accepted that electromagnetic waves were just waves. But you can't explain this using this effect, these observations we've just talked about, using wave theory. Because if the particles were acting as waves, then the frequency of the wave shouldn't affect whether or not the electrons were emitted, because the wave is just transferring energy over time. And if I wait long enough, it should transfer enough energy. The frequency shouldn't have anything to do with that at all. So that's a real big problem if we're using wave theory. The intensity should increase the rate of emission at all frequencies. It shouldn't just matter. It shouldn't only matter once we cross this threshold frequency. If I increase the intensity, I'm giving more energy. So I must be giving them out faster, regardless of the frequency of the light. So again, that's a problem. And the other thing with the waves is, like I said, we're transferring energy over time. So it should be that the emission takes a little bit of time because I have to transfer that energy through the wave. But what we see is immediate emission, which we can't explain using the wave theory. So this experiment is very problematic if you want to treat light as a wave. What was needed was a new explanation. So Einstein came up with an explanation, and he said that the photons that came in, or the light that was coming in, consisted of these packets of energy, photons. And the energy of the photons depended on the frequency of the radiation only, was proportional to the frequency. So E equals HF, which we now know about and we're happy with. He also said that the photons must interact on a one-to-one basis with the electrons in the material. So one photon can only release one electron, no matter how much energy it has. and one electron can only take one photon. So it can't sort of like take lots of low energy photons and then escape. If it can only grab one photon at a time, and if that photon has enough energy, great, it can go. If it doesn't, it can't go anywhere. So the photon energy would have to be above this minimum amount depending on the material. If it was, the electron would be emitted, and any extra energy would be what gave the electron its kinetic energy. So this explanation is actually the thing that Einstein won his Nobel Prize for in 1921. And this is kind of also the birth of a field of physics called quantum theory. Actually, what's quite interesting about the awarding of this Nobel Prize is that at the time it was awarded, the physics community weren't completely convinced that his argument was correct. They thought it was interesting, which is why he got the prize rather than because they believed it was a perfect explanation, which I personally think is quite interesting. So what I'm going to do is just quickly whiz through the two models, so the wave model and the photon model, and some of these observations, and what should happen with the wave model and what does happen with the photon model, so that we can compare and contrast and explain what's going on. So emission of the electrons happening as soon as the light shines on the metal. Well, for the wave model, intense light should be needed in order for it to be an immediate effect. But with the photon model, a single photon is enough to release that one electron. Second observation is that even low intensity light is effective. Well, by the wave model, low intensity light shouldn't have any effect. But with the photon model, low intensity means that there are fewer photons. It doesn't mean that the photons are lower energy, so that works just fine. Next observation is that increasing the intensity of light increases the rate at which electrons leave the material. Well, with the wave model we can kind of get there because greater intensity would mean more energy, so more electrons are released, that's fine. With the photon model, we're saying that there are more photons per second, so more electrons are released per second, so it continues that one-to-one interaction. Next, the increasing intensity has no effect on the energy of the electrons. Well, that doesn't really work with the wave model because greater intensity should just mean there's more energy, so it should just mean the electrons have more energy. But we can explain it with a photon model because the greater intensity doesn't mean more energetic photons, it just means more photons. So we're not increasing the speed of the electrons, we're just releasing more of them. Right, the minimum threshold frequency, well, we can't explain that with the wave model at all because low frequency light should work, it should just work slower by the wave model. But with the photon model, a low frequency photon just does not have enough energy to release the electron. So the increasing frequency, increasing the kinetic energy, with the wave model we just can't explain it, it doesn't make any sense. But with the photon model that works because the higher frequency means that the photons have more energy, so each electron gets more energy and can move faster. So that is the how we've got from wave to particle basically. Now obviously if we've done this experiment, there is going to be an equation to go along with it that we need to be able to talk about. So this is the equation, HF equals phi plus EK. So HF is the energy of the photon of electromagnetic radiation, phi is the work function of the exposed material, and EK is just the kinetic energy of the photoelectrons. So just to say a little bit more about the work function, this is one of those ones you need to get a definition for. The work function is the minimum energy required for an electron to escape from the surface of a metal. So if I gave an electron exactly the work function of energy, it could escape. So it's the minimum energy needed. But I could give it more and it could still escape. So that's why you have to make sure you have the word minimum in there. Now, we've been talking about threshold frequency. Now we might want to be able to actually calculate what that's going to be for a material. And now that we have this equation, we can. Because we've said that HF equals the work function plus the kinetic energy. Well, if I'm only just giving it enough energy to be released, so if I just use the threshold frequency, the released electron would have no kinetic energy because I would be giving it exactly the minimum energy required to leave. so the work function. So that leads me to say that h times the threshold frequency would equal the work function. So if I want to calculate the threshold frequency for a material, I take the work function of that material and I divide it by Planck's constant. Okay, so that is the bare bones of the theory of the photoelectric effect. We're going to look into this in a bit more detail, and we're going to do a lot of practice with some questions on this because there are a lot of things that we can ask. And it's quite a good topic to be able to link ideas from different areas that we've covered across the whole of the syllabus this year. So remember, if you have any questions, just ask when you see me, and I will see you in class.